With electric field, we can define any static electric field as the negative gradient of some other scalar field that we call the potential. We can do this because the curl of E is necessarily zero, and so it is the gradient of a scalar function. For a magnetic field, the divergence of B is zero, and so it can be described as the curl of some vector function, which is usually called A. This vector function is very analogous to the electric potential, so it is often called the vector potential. As a side note about naming, why we use the letter A for this, and really why we use the letters we do for all of these fields, is because those are the letters that Maxwell decided to use when deriving his famous equations. And he did just go through, this field is A, this field is B, this field is, he skipped C because C is the speed of light, but D, E, F is force. Now that did have some happy coincidences. Electric field did get E, and D we kind of backronymed into displacement field. But that's why magnetic field is B, and by the same note, vector potential is A. Also, next week we are going to be learning about the magnetic analog to displacement field, and that's called H. Just a fun fact. Anyway, the magnetic field can be described as the curl of this vector potential. Now, vector potential has a lot of analogies with the scalar potential, including a bit of freedom. With the scalar potential, we could add any quantity we wanted, and we would still get the same scalar potential, or we would still get the same electric fields. With vector potential, because we are looking at the curl of the vector potential, we could, if we wanted to, add the gradient of some scalar function to A, and it would still follow this formula. So how do we deal with that? Well, first, let's do a bit of vector calculus. B is equal to the curl of A. So the curl of B is the curl of A, and that is one of our product rule identities. It's product rule identity number 8 It's second derivative rule number 11 on the inner cover of your textbook. So the curl of A is equal to the gradient of the divergence of A minus the Laplacian of A. And so how do we deal with the freedom that A has? We select an A that is divergentless. Now note, we don't have to do this. We just prefer to because it does make the math so much easier. Because if we do this, the divergence of A is 0, so this whole term goes away. And so the curl of B is equal to the negative Laplacian of A. Now we've also learned that the curl of B is equal to this quantity right here, mu naught times the current density. So the Laplacian of A is equal to the negative mu naught times the current density. This brings another similarity with electric field, because we could say that the Laplacian of electrical potential was the negative of the charge density divided by epsilon naught. Which means that all of the math that we learned to deal with this electrical potential, we can do all of that for vector potential. Now keep in mind this is a vector equation, but because of the way the Laplacian works, the Laplacian acts on each component of A separately. So if we're using Cartesian coordinates, A has an x component, a y component, and a z component, but the x component of A in this formulation depends only on the x component of J. The y component of A on the y component of J, z component of A on the z component of J. So this could be written out as 3 separate equations where each component is treated entirely separately. Now, another result of this analogy is that since the potential, or the Laplacian of the scalar potential depends on charge, and the Laplacian of the vector potential depends on current density, we can basically do Coulomb's law for current now. So for a scalar potential, it was scalar potential is equal to the integral over all space of rho over epsilon naught, rho of r prime over epsilon naught times. This is, I can't do a script r in my sheets, but remember script r is the r vector, that is the r of the point that we're interested in, and r prime is the point where the current is. And when we integrate all over the prime coordinates. So basically, if we were trying to do this for a wire, we would integrate over the wire. R vector would be a fixed constant value, and that would give us the scalar potential at that constant value. Now, as we're going to see in problems, this is not the only way to calculate the vector potential. Again, vector potential has a significant amount of freedom to it. But this is the most common way. This is often known as the Coulomb gauge. And when doing this way, the vector potential will pretty much always be in the same direction as current, assuming current is going in one direction.